My pleasure being here today, and thank you for this very nice welcome. So my name is William Moaro. I'm working for IBM Expert Labs, so in the post-sales entity. And my main line of activity is to help my customer to jump into security projects. So new security project, and my specialty is encryption and crypto. So I did my best, let's say, to help my customers to adopt and to mine the gap of the crypto as fast as possible, because threats are increasing and we have to face new challenges. So today I propose to you a view regarding the network encryption performance, because as network become again a new hot topic, let's say, it's very important to understand what can be done and what may impact, let's say, the performance if you decide to encrypt much more of what you're encrypting today. When I say much more, it's not to say that basically your customers are encrypting a lot their network. That's the fact. So for those deciding to encrypt, most of the time, the issue is...
One moment, Graham. I'm not sharing my user error.
The issue is, what should I select in terms of parameters and what should I select in terms of properties in order to be sure that my network encryption satisfies at least to objective security, of course, but also performance. Because we cannot accept bad performance because of the security. If we can have both together, that is, well, the purpose of these presentations is just to remind what seriously damage and impact the performance by encrypting your network. And so I will remind what I call crypto dimensions, meaning crypto is just not about an algorithm, the key, and then let's go. It can be a little bit more complex. So I will simply review some of the major crypto dimensions so that you have a better idea of the reason why I'm recommending some settings. And because no one trusts me when I say that, I tested all of the possible combinations for the TLS protocol on the mainframe, and then I can show you which cipher switch is better than another one and explain the reason why. That's what I propose to you for today. Okay. So
Does it switch?
No. Okay. This is basically what I said in my introductions. When we have to set up the network encryption, most of the time, the main target is security. This is the reason why we want to encrypt and to protect the data in motions. But if we are not, we don't take care enough about some interesting parameters, then we can miss completely the performance target. It's obvious, but taking care of this will help organizations to be more agile, to push back the design saturation point of your network performance, and also to comply with your internal security guidelines. That's very important. So it's very important to understand what I call the crypto dimensions in order to be able to achieve these two objectives, security and performance. Most of the time, my customers consider that what is important for some crypto is the algorithm, the size of the key, and for those who know what it is, the mode of operations. And for those knowing what it is, the key protection profile, meaning what we are doing with the key. Should we protect the key or not, or can the key be should keep that as is? So that's a good starting point, but it's definitely not enough. Particularly regarding the network, we have to take into account more dimensions. And when I say dimension, it means options. And when I say options, it means that you can combine different of these options in order to perform cryptographic operation for the networks. So confusing, selecting a bad algorithm, not good key size, selecting the wrong key protection profile, selecting the wrong key exchange mechanism, then you can miss your security objective and your performance objective. That's okay? Okay, so I will not go over the 9 crypto dimensions, but just some of what I'm consider very important, particularly for the network. And we will see at the end of this presentation, because I test most of the different combinations, some patterns could be considered as a main takeaway of these presentations. If you recognize yourself with this pattern, then you know what could be done to improve and to optimize the way you are protecting your network with TLS protocol today. So multiple crypto dimensions, and these crypto dimensions are quite similar to what we can find with the TLS naming scheme. So when you are using a cipher suite to protect a network session and their connections, most of the time you are selecting a cipher suite look like this, starting with TLS, then a key exchange mechanism, then the authentication algorithm, then to protect the data in motions with symmetric encryptions and the hash algorithm. So basically, this looks like a good cipher suite, but you have a lot of choice according these different elements of the naming schemes. So when you have to choose, default setting is time to time not the best choice in running on the mainframe. Why? Because the list is the same for x86 Power ARM platform, and we are accelerating an hardware way some cryptographic operation on the mainframe. So this should be reviewed at least once for a performance reason. Second, there are some algorithms known for being insecure or having vulnerabilities. So this is also a thing that you should know before selecting a cipher suite. So this looks like complex, okay? But you have to clean and you have to know the reason why you are selecting a cipher suite versus another. Security, performance, good reason. Compatibility, maybe another good reason. Okay. So I'm gonna focus on different aspects of these crypto dimensions to let you know the reason why and what may be the performance impacts on the Z systems. First item that I want to cover is the simplest one, the algorithm, the first dimension. So there are many types of algorithms that we can use according to the cryptographic objectives we want to achieve. So most of the time, cryptographic algorithms are sorted by family. So symmetric algorithm, asymmetric algorithm, and secure hash algorithm. So the objective of the symmetric algorithm is to protect data. The same key is used to encrypt and to decrypt, is fast with an high bandwidth, and it's easy to use. The issue is that if someone steals the key, then your secret will be compromised. Asymmetric algorithm is quite interesting because you are using a pair of keys. What has been done by a key can be undone only by the other keys. So it's particularly interesting to set the digital trust, digital signatures, public exchange, and so on. So it's efficient, but it consumes a lot of CPU cycle. And so we have to use such algorithm for well-defined purpose. Hash algorithm, it's about digesting and creating a sort of fingerprint for data. And the combination of these different algorithm family can help you to achieve interesting objectives regarding the security. So basically,
I have a question.
Yes.
Chat.
That's a good question. It depends. Today, sorry. The question is, TLS ELS 256 DCM SHA 384 is considered the strongest of all.
Is that question?
No, because as you can see, I have to go back one slide. As you can see, implicitly, it uses the key exchange mechanism, which is everything. So there is one particular crypto dimension that is not satisfied and that is not covered here. It's the secure key exchange mechanism that protects you against the corruption of your session if someone steals a private key. Then it can corrupt all of the network connections flowing into a compromised sessions. So we need something like ECDHE or DHE using ephemeral keys as the key exchange mechanisms in order to be sure that this cipher suite become the stronger that you can use. As of today, the use of ephemeral keys for the key exchange mechanism is not mandatory. When I say not mandatory, it's considered as optional if people want to have the maximum security. But with TLS version 1.3, it will be mandatory. But as it is an extra mechanism, it has a cost. And if it has a cost, sooner you mind the gap and you are accepting this cost in your production, better you will be when TLS 1.3 will be the standard with the sunset of TLS 1.2. So this is a thing that I will come on later. So we cannot confuse and select an algorithm and replace it with another one without taking care of what we are doing. So symmetric algorithms have their own performance profile according to the code that is executed. So DES behave different way than DES. And on Z systems, we are hardware accelerating like L, the AES algorithm. So for symmetric encryptions, no options, AES, no matter what. Okay. For the rest, MD4, SE4, the past and the legacy symmetric encryption algorithm, the bandwidth is somewhat a penalty today. So this is not an option, and they are not secured anymore. So this slide is simply to show you the difference in terms of performance comparing the different algorithms. So we have to select those being hardware accelerated by OZ systems infrastructure. The second important crypto dimension to take into account is the key size. Longer is the key size, better, more secure is the encryptions in regard of the brute force in order to intuit or to find a key we don't have. So that's a way to extend the lifetime also of encryption, simply increasing the key size. Selecting the appropriate key size is very important. Too big, too long, then it damages your performance. Too short, there is no security. So you don't have to be creative, and you simply have to comply with what most of the IT security guidelines recommend you, from the UK NCSC to the PCI DSS or whatever. It's quite interesting to see that they are more or less agree on what should be used in terms of key size for today or up to 10 years from now. But nowadays, it includes also a view regarding the quantum era and the quantum computing risk for several algorithms. And this is a thing that we can talk about later. So of course, key size matters. And in a second, you will see that with the same algorithm, increasing the key size, then the performance is become not good. So in terms of gigabyte per second, with the central processor, with AES, simply increasing the key size from nearly 5 gigabyte to 3.5 gigabyte per second, the bandwidth goes down. It's more important for asymmetric encryption or asymmetric algorithm family like RSA, as you can see, from nearly 100 operation per second for key generations to 2.38, which is quite small. So that is important to take this into account. Public key is important because this is embedded, the public key is embedded in the digital certificate, and the use of the digital certificate and the properties of the crypto of the digital certificate will also impact your performance. We will see that later. The third dimension is what we call mode of operation. Who knows what a mode of operation is? Okay, so it's a thing that is studied at the university since the 70s, and the concept is quite simple. We have data that big that we have to push into a network pipeline that big. So the first thing we have to do, as we did with Flat5, is to split data into blocks. And each block will be encrypted with an encryption key. Okay, but if it is the same encryption key, so if the data needs to be encrypted is the same, the output or the result will be the same. Then the encryption is at risk because repetitive pattern may be a need or a breach for your encryptions. So this is why we designed it in the past. The concept of mode of operations, it's an additional logical between the encryption of each block in order to be sure that there is no possible pattern that can be identified, let's say, through of an encryption operations. So there are many of these encryption patterns named mode of operation that exist. At first, no mode of operation means each block is encrypted the same way. The block of data, the key, and then I'm encrypting the next one. This mode is named electronic codebook. So the simple one. It's maybe a serious issue in terms of security, and we will see that later, particularly because of repetition of data that may open some risk. We have the CBC mode of operation, which is quite interesting. We are taking a piece of the data that has just been encrypted to encrypt the next block of the data. Then we are chaining the data together in order to be sure that it's randomized, let's say, what the data encrypted look like at the end. I have a small drawing to make this more explicit. If I want to encrypt these pictures of the Sierra Nevada, simply using the algorithm AES and the key size of 256, the result will be 0. Repetition, all of the black pixel will turn to blue, I don't know, and all of the white pixel will turn into, because of repetitions. Each block having the same data will be encrypted the same way. That's the issue with electronic codebooks. This is why this additional logical, the mode of operations, and we have a list in the bottom, needs to be used in order to guarantee that the encryption process achieves the objective of the confidentiality. It looks like easy, presented like this one, but it's very important because the cipher block chaining is different from the cipher feedback block chaining and so on and so on. It's different logical behind. And their behavior on encrypting and decrypting the data are not the same, and the performance. So this is very important to take this into account. This is an overview from the Z16 performance test I was able to run. The CBC, the way it chains the data together to perform the encryptions is twice or 3 times slower in encryption compared to decryption. So as a server, if the client connects to you and you are using the CBC cipher suite, you know that you will be limited in bandwidth simply because as a server encrypting the data for the client, you will reach the limit. And that is the behavior of the mode of operation on top of the encryption algorithm. CPRs, ECB, CCB should not be used because it's what I just showed you earlier. XTS is for dataset, ZOS dataset encryptions, file systems encryptions, volume encryptions. So it's fast and symmetric in terms of encryption and decryption performance. CFB and CTR is way behind, but it's used only for several types of What I want to talk about you now is the key protection profiles, because when we try to seek for performance and security, we need time to time to think about, do we have to protect the encryption key? That's very important. The encryption key can be found into the clear as is. If I dub the memory, the ZOS, or for my Linux on Z systems, or should be protected by another key, a wrapping key, or a master key. The master key resides on the Crypto Express card. So with the double encryptions to protect the key, then you have also an impact. So 3 possible key protection profile. The key, in the simple way, you are not protecting the encryption key at all. So it can be found into the clear in the operating system memory or into files. So the security is not that good, but the performance is pretty good. Then we have secure key from the Crypto Express card. It's doable, it's possible. The security is maximum thanks to the double encryption, but the performance is quite a mix of turtle rabbit, much more turtle, but it's low. Then the protected key, it's an hybrid mode. The first encryption is done with secure key, and the next encryption operation will be supported by the CPACF. So with a wrapping key, and the bandwidth from the memory to the central processor is faster than the bandwidth from the PCI Express bus. That explains why the bandwidth will be different. So here it's a Rabbit 2. The same algorithm tested with different key protection profile look like this. With clear key, AES 128 CBC, 5 gigabytes of encryption per second in encryption. With protected key is nearly 5 gigabytes, but with a Crypto Express card, it's 213 megabytes. Between gigabyte and megabyte, you have a difference in terms of bandwidth. So we should not confuse regarding this. It's very important to select the appropriate mode and to be sure that more objective comply with the needs of security, or if the security is good enough with the alternative for encryption operations. The key exchange is quite important dimensions. It's quite important for the performance because it's an extra mechanism that it's a mechanism that is implicit based on RSA algorithm in order to create a session key that will be helpful to encrypt the data in motions, let's say once the host is set after the handshake. So there are multiple key exchange algorithms, RSA. Most of the time it's the standard one, Diffie-Hellman, Diffie-Hellman ephemeral, elliptic curve Diffie-Hellman, and elliptic curve Diffie-Hellman ephemeral. So most of these algorithms support the latest version of the TLS protocol up to TLS 1.3. But as we can see with 1.3, only the most advanced key exchange mechanisms are supported. This is important because as of today, the standard is TLS 1.2 and TLS 1.3. And what I observe with my customers is a mix between advanced key exchange mechanism and trivial or implicit key exchange mechanism. The risk is when we will change from TLS 1.2 to 1.3, you have to face a protocol shock in terms of project. You have to change, to switch. But you did that many years. It's just another protocol version to change. But you have to review your sizing and your capacity planning of your LBARs, because if you didn't adopt yet an advanced key exchange mechanism supporting the perfect forward secrecy, then the step in terms of capacity to perform exactly the same amount of transactions will be high. More CPU, more crypto cards. This needs to be anticipated. Okay. So what I did is I tested the different difference between advanced and trivial key exchange mechanisms, the RSA1. So this is the same cipher suite. This one does not support the PFS property using ephemeral keys, meaning the ability to ensure that if a session is compromised, the other connections will not be, because the key is ephemeral. So you steal a key, but this key is for one-time use. There is no risk. But this has an impact. And if you are using elliptic curve Diffie-Hellman ephemeral, elliptic curve Diffie-Hellman ephemeral with RSA, or with an RSA digital certificate or an ECC-based digital certificate, you see that the impact of performance is very important. So if your standard is there for TLS 1.2, the standard of TLS 1.3 is there. So you have to be prepared, let's say, to see your bandwidth being reduced, or the number of operations you can perform per second being reduced. So I'm warning my customers since a while regarding that when TLS 1.3 will be mandatory, and the unique one we should use, some of my customers will have an issue. So we will come back on this later. There is an excellent document from the communication server team of IBM reporting and describing this phenomenon with additional performance tests. So if you Google this, or if you click on the link from the presentation, you should be able to get some more about this. With TLS 1.2 and 1. So it's time to share with you fruits of a test campaign. So what I did is I decided to test all of the possible combinations. When I say that makes sense, I remove from the list things that should not exist anymore on a client implementation. MD5, for example, the thing from the past, triple des and null encryption. Null encryption means no encryption. So, okay. DTLman anon also. So I remove a couple of things, but I keep, let's say, Camellia, Aria, and others, just to show you what will be the impact if we decide to use also non-optimized encryption algorithm. So this is why I did. It took me a month, but I test all of the combination. And what I'm proposing you right now is to see all of them sorted by the best to the worst. And then we can open discussions. So my environment, Raccoon is me because that's my nickname. I'm testing. Okay. So what I set up is an injection machine, it's quite powerful enough in order to see something from the mainframe and particularly from the crypto express cards. What I wanted to test is both the N-check and the bulk assessment, despite it's just a few amount of data that I want to bring back during the TLS connections. I tested also SCP and SFTP from the SSH protocol, so I will show you the result. And the target machine was a Z16, ZOS 2.5, and I needed a URL which is protected from the ZOS, and I decided to use ZOSMF. Because ZOSMF, once well configured, can offload all of the cryptographic operations to ICSF and to the crypto card and the CBACF. So that was quite interesting as a target, let's say, to check what will be the performance impact of all of these different combinations to the Z systems and the ZOSMF applications. So, okay. Some information about my test case. The injector didn't change. I tested one cipher suite at a time, and I run 3 times, let's say, the test just to be sure that I'm observing exactly the same thing. I'm not polluted by other activities. So I did that late in the night in a system that is not production systems at full speed. So that was okay. Regarding the test, it's about 2 minutes, full check and no reuse. So I didn't reuse the sessions. I simply tried to assess what will be the impact in the worst case where we have to negotiate again a full and check for each connections. For the SCP and SFTP, I try, let's say, to bring back or to put a 5 GB file and assessing the different cipher suites according to the time and to the bandwidth. I use different digital certificates with different key size. So what I use is the Racket default settings. So when I say 2K with shade 256, RSA 3K with shade 256, and RSA 4K. This is important because the same cipher suites, let's say, we have different performance if the digital certificate used by the server to authenticate itself use public key material that are quite long or quite short. So I had to test, I don't know, between 20 and 30 cipher suite multiplied by the number of digital certificates. So that's a huge amount of tests that I was able to. That's the only way I can conclude with these different dimensions. So for those over there, it's good to see the screen that is the closest to you, because we can see in the first part of this slide, let's say, I rounded everything to 100 to make things easier. Otherwise, 22K SSL and check, TLS and check per second to 0 was not that good. So I simply rounded to 100. And we see difference. We see difference for the first part that does not support perfect forward secrecy. So the key exchange mechanism with ephemeral keys. This is a cipher. These are ciphers that are performing, but there is a risk here regarding the switch to TLS 1.2 to 1.3, because if you switch that to that, the performance impact will be high. It's good enough for today. I mean, for TLS 1.2, the use of ephemeral keys is optional today, but that will be mandatory tomorrow. So that this should be helpful to answer the question of the the gentleman from the chat. You see the performance impact of the size of the data, let's say, running from the bulk assessment, so after the uncheck, and you have also an overview with no data that has been changed, so it's a pure SSL uncheck. That is interesting because clearly we see the impact of non-ephemeral based key exchange mechanism. And then we see that GCM algorithm is always faster than CBC algorithm. So the GCM mode of operation is also what is important to drive the performance to the next level. SHA-1 is also interesting. SHA-1 is different of SHA-2, it's different of SHA-3. It's a different logical behind because it's a fruit of a contest and the winner has the right to have the name of SHA something. So it's clearly not the algorithm behind. And SHA-1 is 3 or 4 times slower compared to SHA-2. So there is no reason to keep SHA-1, but compatibility, backward compatibility. But you have to trace and you have to notify each time SHA-1 is used because clearly it start to become old and obsolete. There is another thing important. In terms of key exchange mechanism using ephemeral key, elliptic curve diffie and ephemeral keys are twice faster compared to diffie and ephemeral. So if you have a choice, switching from this to something here, then better to use elliptic curve diffie ephemeral than to avoid a gap which is too huge. Like with this slide, I split it into 3 with a focus on the different digital certificates with 2K size, 3K size, 4K size, just to be more visible. So today the standard is a public key size of 2K. Some are already using a 4K size for RSA, which is good, but the performance impact is also there. Okay, so I think we reach a limit where we will not be able to increase the size of the public key for RSA. It's probably a good opportunity to change, and with the quantum safe algorithm that will be announced and supported by design by default with the next versions of the TLS protocol, maybe we will find an hybrid or a new one that may satisfy the security needs and the performance needs. The RSA is at the end of its road, clearly. I didn't provide you the view with elliptic curve-based digital certificate for one reason, because we can speed up elliptic curve cryptography from the silicon on the chip, so the processor units, the CPACF, or from the crypto cards. And I fall in a situation where everything was on the CPACF. So my CPU is like hell, despite the bandwidth was quite good and the throughput was quite interesting. So I need to redo my tests, ensuring that it is redirected also to the Crypto Express card so that I can come back to you maybe next year with a good overview with the 2 possible configurations to support elliptic curve encryption. So it was important doing this test to be able, let's say, to check what I'm doing. And the new SMF 8230 subtype 31 was quite helpful because with this SMF record, I can see my target application, so EZU server, so ZOSMF, and I can be sure that what has been done from where in terms of engine, so the Crypto Express cards, the CPACF, and what algorithm were used, and also what ICSF service was invoked. So to control, to check, that was perfect. That was not the only tool I used. RMF report, crypto report was quite interesting also to see at the machine level what I did with my crypto cards and the remaining resources that I have. ICSF display command was quite interesting also because recording /d ICSF cards, I was able to see the number of requests towards my Crypto Express card being implemented. So that was a good way to check if my injections was working properly without waiting for the 2 minutes of the test and and dumping my SMF record. Another thing that is important also is using the HMC. Thanks to the API or directly with the dashboard history display, you can select a particular adapters or all of them, and you have an idea of what you are doing for a given Crypto Express adapters, which is cool to check the design saturation point with a 15-second interval of your crypto adapters. So I was able to claim to 20K, 22K SSL uncheck per second, and I was able to check the use of the Crypto Express scans. In terms of CPU or processor usage, with the HMC, I was able to check and to see, let's say, the LPAR usage. So with my RSA test and ECC test, and as you can see, the ECC test was not covered by the Crypto Express card. It goes directly to the C packet. So that's why my processor usage was quite huge and big for this test. But for the RSA, that was interesting to see that the Crypto Express cards play its role as an accelerator to offload, let's say, the computations from the central processors to the crypto cards. The last test I did was about the SSH protocol. So basically, SSH is very important because it includes the SSH connections to connect to the mainframe, the SCP, secure copy, or SFTP to get or to push some files. And one more time, cipher suites matters. And we can see here, rounded to 100, the difference in terms of CPU consumption, no, in terms of times and in terms of bandwidth. So in black, the bandwidth, the best one in terms of bandwidth was the EOS 128 GCM. And the worst was JJ20 Poly. This one is not hardware accelerated by the platform. So in the cipher suite order, it's important that according to your security guidelines, you put into the right order the cipher suite in order to claim fast transfer and secure transfer. Or secure transfer that is fast enough. Let's say it depends on your logical, but it's important you are doing something. Otherwise, if this one is picked up at first, then your performance will not be good. Your security objective will be achieved, but the performance will be a disaster. Okay. So this ends this presentation. I hope that you discovered and you learned a couple of things. As a conclusion, beware of default settings. It's very important to review cipher list and the order. Otherwise, you may achieve the security objective, but the performance objective will be lost. To think about both security and performance, to remind what may impact your network encryption performance. TLS, don't forget to have a brainstorming about PFS for today and tomorrow. This is what I said. TLS 1.2 does not mandate to use ephemeral keys for the key exchange mechanism. But that is not the case for TLS 1.3. So sooner you jump in, better it is. And to check if the offload of the cryptographic operation goes well on CPACF and on the Crypto Express cards. 2 links, plus a third one that will be released really soon. So each time we are releasing a Z Systems machine, there is a benchmark, an official one from IBM, where the performance is well documented for all of the cryptographic operations. And the one regarding the Z16 and the Crypto Express 8S will be released very soon. So I will keep you posted about it. Thank you for your attention. Any questions?
Thank you. That's very interesting. Can I ask you, the tests that you did were from one ZL part to another ZL part? Is that correct?
From a Linux LPAR to a ZL par.
Okay. So a Linux on Intel or a Linux on?
Linux on Intel.
Right. Okay. So is the other thing that you need to involve in the choice of algorithm and the choice of mode is what is supported on the other server?
Oh, yeah.
So, it's quite possible the other server will run the fastest algorithm here much slower, and it will be the wrong algorithm to choose.
The question was about the injection technology I used. Was it a mainframe or x86? And the reason why of the question was about is it important to take into account, let's say, the multitude of processor architecture in the choice of the cipher suite orders, because maybe with x86 or another processor technology, the performance impact will be different. Yes, it's true. At first, for compatibility, the cipher suite will work the same because of the standard. On the symmetric algorithm, AES is the standard because it's hardware accelerated by the Intel processor with the AES NI instructions. The same for AMD. And the SHA algorithm with SHA-2 also is hardware accelerated by the processor. You will have no issue on that. For RSA or elliptic curve cryptography, I would say the performance impact is the same between x86 and Z systems. So there is no real difference, but if the client machine has crypto adapters, I don't know, like the Crypto Express card, for example, then because of the technology, the performance may be different with elliptic curve cryptography and RSA. So my feeling is the nature of the digital certificate is much more dimensioning in terms of performance than the technology of the client. The processor architecture of the client connecting to the mainframe.
I found the results quite stark. The difference once you go to perfect for security. Yeah, it's the important point.
Thank you.
No, sorry.
As Danny says, the ephemeral keys do seem to have a significant impact on the performance. Are customers who are moving to TLS 1.3 actually experiencing?
I have a slide on this for this afternoon. As of today, on the volume of network session I analyzed with my security assessment, I would say less than half of a percent of network session are TLS 1.3 protected today for the mainframe customers.
It answers my question.
Two custom, in fact, on the last 36 technical study on the network I did, only 2 customers supported TLS 1.3 for a few amount of network sessions.